Now, the integral test is flexible. If you start at n equals 2, it still works. So that's flexible. Because if you think about what f does, f is positive, continuous, and decreasing. So it looks like this, right? Goes downhill from left to right. Here's the x-axis. Here's the y-axis. In the statement of the theorem, we start looking underneath the curve at x equals 1, right? And so what does the integral represent? If the curve in red is f, what does the integral represent? The area, right? And so if that integral, if that improper integral converges, then that means the area underneath the curve is finite, right? But let's say we, instead of starting at 1, we start at 2. And then look at the area under the curve from 2 to, infinity. Not that you ever get to infinity. If it's finite from 1 to infinity, won't it be finite from 2 to infinity? Yeah, does this little bit of area affect whether or not the area under the curve is finite, in other words? It doesn't, not even a little bit, right? Because that's a finite area right there. It's the tail area, it's the area under the tail of the function that determines whether or not the integral converges, whether or not the area is finite or infinite. So my point is this: where x starts doesn't matter. Doesn't really matter. The integral test will hold, okay, as long as f is positive, continuous, and decreasing. Okay, what is f of x? 1 over x natural log x. Okay. So, number one, is this thing going to be positive? F, I'm going to make the statement, and you guys tell me why. F is greater than 0. Why? By the way, why did we have to start at n equals 2 here? What's the natural log of 1?
0.
Yeah, so that would create a problem. Are we going to have any issues with f being positive? No, because x, now think about it. X is going to go from 2 to infinity, right? X is going to be bigger than or equal to 2. Certainly this factor, x, is bigger than or equal to 2 if x is defined to be bigger than or equal to 2. And so is the natural log of x, right? Once you get past x equals 1, the natural log is positive. So it's not an issue. You could just say f is greater than 0 since both x and natural log of x are greater than 0 for x greater than or equal to 2. What's the next one? PCD. Continuous. Okay. X is a polynomial function. It's a monomial. The natural log of x is one of those transcendental functions you learn about. You know it's continuous. And we're taking the product and then taking the reciprocal. So we're taking the product of x, natural log of x, and we're taking the reciprocal. The product of two continuous functions on the interval from x is greater than or equal to 2 is continuous. The reciprocal is going to be continuous as long as you don't get division by 0, and you won't. So it's clear f is continuous. And if you want explanation, you could say since the product of x and natural log x, well, I guess to be very careful here, I could say this: since x and natural log x are both continuous. And then if you really wanted to be meticulous about it, you would say, and the product and reciprocal of continuous functions is continuous. On the relevant domain.
Now what's the relevant domain here? Yeah. So f is continuous since x and natural log of x are both continuous on or for x greater than or equal to 2. And then positive continuous and decreasing. So I suppose we could take the derivative. F prime x. Hey, just for fun, we don't have to use we could use the product rule, just raise x natural log of x to the -1 power. But I think it's easier to use the quotient rule. And I think it's fun to say low d high minus high d low. So what does the quotient rule say here? Low d high. Well, the low function is x natural log of x, but what's the derivative of the high function? 0. So that guy disappears entirely. That's nice. Low d high minus high, which is 1. D low. Oh, darn it. Product rule. X times two functions multiplied together. Product rule. So depending on how you like to do it, you can take the derivative of the first times the second. So that gives us 1 times natural log of x plus the first times the derivative of the second plus. Oh, you're right. Or x times 1 over x, however you want to write it. Either way. And then all that is over x natural log x squared. So this isn't going to be so bad, is it? So this whole thing's 0. We've got a negative up here. And what does this become inside the parentheses up top? Okay. So is the denominator always positive because it's squared? You bet. What about the numerator inside the parentheses, natural log of x plus 1? Always positive. So you're taking the opposite of a positive number, right? So it's less than 0 for x greater than or equal to 2 is all we're interested in. That's definitely true. Which means what about f? So f is decreasing. That's not so bad. I've seen worse. So we've got it. Positive, continuous, decreasing, which means what? We can do the thing. We can do the it. Thus, it, the integral test, applies. And you get to review integration. Yay! So we're going to integrate f, which is 1 over x natural log x. The integral, what's the integral going to go from, though? 2 to infinity. All right, so let's think about it. What would be the best technique to use to integrate this thing? So you could take the time out here and just find the antiderivative. I'm just going to go ahead and write the limit. Oh, was it 1 over that? Yeah. I just noticed that I didn't put in the numerator. Okay. So the limit as what goes to what? B goes to infinity of the integral from 2 to b or not to b. 1 over x natural log x dx. Okay, so could we use u substitution maybe? Yeah, it's all right there, you guys. If you need to see it, if you need to do the u substitution, actually put in u, you might want to do the timeout thing. But if you don't mind just pretending like you did it, it's not so bad just leaving it as is and maybe rewriting it like 1 over natural log of x. And then write the 1 over x dx separately, because this guy, 1 over x dx, if you let u equal natural log of x, 1 over x dx, there's your perfect du. It's good to go. And then what is this really right here? This is really, yeah, u to the -1 or 1 over u, yeah. But don't actually make the substitution, because then you have to change the limits of integration. You don't want to do that. So, oh, that's interesting. So what do we get when we integrate 1 over u du? Natural log of u, but u is the natural log of x, so what do we get? The natural log of x. That's the antiderivative. Let me put in all the other stuff. Isn't that fun? Put in the evaluation brackets, and we go from 2 to b. Does that look right to you? Limit b goes to infinity of the natural log of x, evaluated from 2 to b. Yeah? Okay, so now do the evaluation before you take the limit. And you get what when you plug in the upper limit? Natural log of the natural log of b minus natural log of the natural log of 2. Isn't that fun? Okay, so b is going to infinity, right? Just evaluate it from the inside out. What does the natural log of b, this inner function, do as b goes to infinity? It goes to infinity. Slowly, but it goes, right? So what is the natural log of some function that goes to infinity going to do? It's going to go to infinity. So the big picture is this guy is going to go to infinity. And then this guy has no effect on anything. So what are you going to say then? It diverges to infinity. Okay, so thus, what about the original series? Yeah, n equals 2 to infinity of, what was it, 1 over n natural log n. Diverges by it.